We have a finite amount of time and a list of tasks that each offer a different reward. If every task takes exactly 1 hour to complete, but you only have 3 hours total, how do you mathematically guarantee that you walk away with the absolute maximum profit? Imagine a room with 3 chairs. A group of students arrives, and the rule is simple. The students with the highest marks get to pick their seats first. If a student's favorite chair is already taken, they check the next available seat. If every chair is full, they have to leave the room. This exact logic drives the job sequencing algorithm. We have 5 jobs, labeled A through E. Every job requires exactly 1 unit of time to complete. Our maximum deadline across all jobs is 3. This means we only have 3 time slots available to schedule our work. Sorting out which jobs get those 3 slots isn't a matter of guessing. We can solve it by translating our natural intuition for prioritizing high rewards into a strict set of algorithmic instructions. It is tempting to look at tight deadlines and try to schedule those jobs first, but the greedy approach tells us to ignore the deadlines initially and look at the value. Greedy algorithms always secure the biggest immediate reward. To program this, our first step is to sort the entire list of jobs from the highest profit to the lowest profit. Now we evaluate our top priority, Job A. It offers a massive profit of 100 and it has a deadline of 2. That means it could theoretically fit into slot 1 or slot 2. Here is the defining rule of the algorithm. Always place the job in the latest possible empty slot before its deadline. If we casually threw Job A into slot 1, we would occupy early time that might be the only option for a future job with a deadline of 1. By pushing high-profit jobs as late as possible, we keep our early schedule clear for tighter constraints. Next on our sorted list is Job C, with a profit of 27 and a deadline of 2. It wants slot 2, but Job A is already there, so Job C moves 1 step backward, checks slot 1, finds it empty, and locks in. Now we hit Jobs D and B. They both have deadlines of 1. Their latest possible slot is slot 1, which is now occupied by Job C. Since there are no earlier slots to check, both of these jobs are rejected. Finally, we evaluate Job E. It has a deadline of 3. Slot 3 is wide open, so it takes the final seat. When we translate this bouncing and sliding into code, it becomes a simple decrementing loop. The computer sets a variable to the job's deadline, checks if that slot is empty, and if not, steps backward towards slot 1 until it either finds a space or gives up. Let's test this logic. Here is a new set of jobs, already sorted by profit. Pause the video, trace the backward loop for each job, and determine the final schedule and total profit. Let's check your work. J1 takes slot 3, J2 takes slot 1, J3 takes slot 2. The correct schedule from slot 1 to 3 is J2, J3, J1. Adding their profits together gives us exactly 90. This specific backward searching loop is what allows the algorithm to dynamically navigate rigid time constraints without ever sacrificing the highest possible rewards. Returning to our original dataset, we can compute the final total. Job C yields 27, Job A yields 100, and Job E brings 15. The maximum profit for this schedule is exactly 142. If you need to map this out on an exam, you can reconstruct the entire logic from 5 letters, JSSLP: jobs, sort, slots, latest slot, profit. When tracing this on paper, students regularly make 3 fatal errors. They forget to sort the list by profit first. They fill the earliest available slot instead of the latest. Or they try to cram 2 jobs into the exact same 1-unit time slot. Avoid those mistakes, and your schedule will be flawless. Because we sort the array up front, the sorting phase dictates our base time complexity, putting it at big O of n log n. We'll break down the exact slot searching complexity and trace the formal mathematical proof of this greedy choice in the next video. By combining greedy value selection with delayed chronological placement, the job sequencing algorithm guarantees the absolute maximum return on a finite resource.